scientific session. So I request once again Dr. Rupjyoti Gogoi to take a sincere. So if all over there, please, I would like to hand over to Dr. Rupjyoti Gogoi. Please.
Uh, Thank you, Sanjeet. Good morning, everyone. Am I audible?
Yes, yes, madam. We are audible.
Okay. Good morning. Actually, Sanjeet, there are two session chairs for this session, Munmun and myself. So we had a discussion among ourselves. First of all, she will be sharing the session till 11:30. Then I will take over. So, Munmun, I will request you to start the session.
Actually, it is okay if you continue. Like if you are
No,
not
no.
around, sometimes I can take over. That is fine. I am
Okay.
there only.
Okay.
I'm sorry. Last times I tried so to reach out Dr. Monmol Devi to request. So
No, no, it's fine. It's fine. Actually, the thing is like two chairs might get confusing
okay,
sometimes. So
okay,
maybe I can be here
yeah.
as a backup. It is
Uh,
okay.
oh, okay. So I request Dr. Gugoi, please to take over.
Okay, Sanjeev. Okay. Thank you, Munmun. Well, a very good morning to all of you. Welcome to the second day of NEMA-VII. It's really a pleasure that NEMA is continuing and we are participating in NEMA-VII. So it's a privilege for me to share this session because we have so many people who are associated with NEMA since from the beginning, and they are speaking in this session, like Kimadri sir, Gulab Sa, Tanuj. All of you are associated with NEMA since from the very beginning. So it's really a matter of pleasure for me to share this session. So the first talk will be delivered by Dr. Himadri Das from Assam University. He will be talking on the UMOF effect in dust aggregates. So, sir, I will request you to deliver your talk. You have 45 minutes.
Okay, madam.
Thank
Yeah,
you.
so thank you very much, madam. And first of all, I would like to congratulate
Hello. Hello, is there everything okay? I am not able to hear.
sorry, I got disconnected.
We can't hear you.
Am I audible, madam?
Yeah. Now you are audible. Yeah, please. Yeah,
Okay,
continue.
so
Yeah.
first of all, I would like to congratulate you for your new assignment in Astronomical Society of India.
Thank you.
And
Thank you so much.
okay,
Congratulations.
so a very good morning to all the respected members of NEMA. So this time we were thinking to attend the event in Arunachal Pradesh because this is the only state left which I have not visited. And we are also planning in the first week of January. And some of my scholars also booked the ticket. But anyway, in that stage, because of this Omicron, we have to cancel the plan. And now we are in virtual mode. But anyway, so that doesn't matter because all of us are in the same platform. Today, actually, I'll be going to start my talk. And the talk will be basically already Rupjyoti madam mentioned about the topic. It is a UMO effect in aggregates. So, is it visible?
Yeah, it's visible.
Okay, thank you, madam.
You can make it full screen, I think.
Yeah.
Yeah, okay.
Okay, so this is my topic, the UMO effect in dust aggregates. Before going to this topic, let me tell you that I'll be working in the small bodies of the solar system for last 20 years. And basically, the small bodies in the solar system, they look small, but they have a very large impact in the scientific community. And these small solar body systems are basically comets, asteroids, meteorites, all these things. These particular objects which are floating on our solar system, dimension may vary from 1 millimeter to few kilometers in size. Many such bodies are there in the solar system, but why they are very interesting, because if we study those objects, then it will give us information about the origin of solar system. Then that is very even origin of planets and other things. And the most important part is that all of you know that some of them are hazardous. Hazardous in the sense that they may collide with our planet Earth also in future. So you probably have heard about near Earth asteroids. So every year, many asteroids come very close to Earth, and they just passes by. And all of us know that in past also, dinosaurs disappeared due to the collision of comet or asteroid with Earth. That's why the study of asteroid or comet is very, very important because of our civilization. And we are now trying to find out a technology whether we can stop those comets or asteroids to collide with Earth. But still today, we are far away from that technology, and we cannot actually we don't have any technology so that we can divert the orbit of a comet or asteroid which is coming to our Earth. So anyway, so NASA had a special search campaign, which is near Earth asteroid search campaign. Every month, you may visit NASA's website for near Earth asteroids, and they always tell us, they always try to detect all these objects which are coming very close to Earth, and only they can alert you that very close asteroid is coming. Sometimes big meteorites also, you might have seen the flash of light in the sky, night sky, and we call them star falls, falling stars. But as I'm telling you that whenever our solar system was formed, that time these comets, asteroids, and meteorites were formed. Okay, so if we study comets or asteroids, then it will give us information about the what happened within 4.5 billion years ago when our solar system was formed. And these are unprocessed materials, and that's why the study is very, very important. Whatever object or materials you see on Earth, these are all already evolution took place, and we don't have uh, actual materials which were there during 4.5 billion years ago. That's why if you get a meteorites on your way to, suppose you have noticed on meteorites, immediately you call Indian Meteorological Society or the Physical Research Laboratory, because these are very important for scientific community to get a portion of all those meteorites. So today, I'll be going to start the effect in dust aggregates. I'll tell you one by one what are the names, because these names are maybe new to you. So before going to start, first of all, I'll give you a brief background of my study. That is, he is basically a Russian astronomer. So he, in the year 1905, described that the linear polarization of the scattered light of an object correlate with its reflectivity. That is, brighter the object, the lower the linear polarization of the scattered light. A very simple formula or simple relation he has actually basically here put forward. And that relation is the scattered light, the polarization of the scattered light is inversely correlated with the reflectivity. More the brighter the object, lower is the linear polarization. And this phenomena was later studied by some investigators, and they have applied to lunar regolith. Means they had taken the data from moon, and then they wanted to study those heat effect. And later, some researcher like Zhukov and Dolglos and Martins, they had studied uh, this effect, and particularly Jupko studied cometary halos, and he found a albedo of 0.1 to 0.2. I will actually define what is albedo, what is polarization in later part of the slides. And Jupko also in 2017 he analyzed that the airborne polarimetric measurements of atmospheric aerosol. He had applied this formula to atmospheric aerosols, and he concluded that polarization maximum 50%, which corresponds to very dark aerosols having geometric conditions. So here the main objective of my study is to study the effect of porosity in the Omo effect for the first time using the aggregate dust model, and we will also study the effect of size parameter of aggregates and effect of composition are also studied. So I'll tell you what are basically aggregates. So the important point is that whenever we talk about cosmic dust is everywhere. Right from your place to my place, dust is everywhere. Dust is dominating the this universe. Though very small percent of dust is there and maximum is gaseous particles, but if you look at different corner of the sky, you'll find the dust particles are there. And for coagulation of these particles, this dust is very important. Even for star formation, this dust plays a very important role. And these cosmic dust particles are derived from a variety of sources. It comes from interstellar grains and the debris from comets, asteroids, and the planets, and possibly their satellites. So these are collected. You can see in the image the collected samples of this cosmic dust. It just look like a cotton. And these dominant sources of IDPs on Earth are asteroids and comets. There is small but still not negligible amount of dust coming from all other sources. And this look like a fluffy materials, and the sizes are very small from some 0.1 micron to 10-20 micron.
Excuse me.
Yes.
I cannot see your screen moving. Are you moving the screen or you are? I'm sorry for asking.
Screen is not visible.
Yeah, screen is visible, but it is not moving. I hope you are moving, but I cannot see it move.
The slides are not changing, he's saying. Yeah, now it is changing, yeah.
Let me try again. Now is it visible?
It's visible, but earlier the slides were not changing. That's what Indu mentioned. Aman.
We have, means it is not even in full screen, I guess.
Yeah.
It is better if I go for this small scale.
Oh, yeah.
Is it visible now?
Yeah.
Now I think it is visible. So maybe some problem with there.
No, it's
So,
visible. Yeah. It's visible.
Now, if you allow me,
Okay, thanks.
person,
Sorry.
in that screen. So can I continue?
Yeah,
This
please.
Yeah.
Yeah.
Thank you, madam. Okay, so basically, cosmic dust is cosmic dust is basically derived from a variety of sources, including interstellar grains, debris from comets, asteroids, and the picture, as I was mentioning just now, these pictures are taken from these pictures as original dust particles which are collected from comets or asteroids, and you can see that the size of this comet dust is very. It looks like a very fluffy things, and that's why the concept of fluffy dust aggregates concept is coming. And this fluffy dust particle aggregates in the solar system appear from collision between comets. And this was actually observed in the debris disk around the young star Fomalhaut, performed with the NASA ESA observatory. And this suggests that the disk contains fluffy dust, which probably occurred from cometary collisions. So these are more common. And later, in many missions, it was found that the cometary dust or asteroid dust particles are basically look like this fluffiness is there. And whenever we talk about fluffiness, then porosity is a very important parameter. Why porosity is very important parameter? Because porosity decides about the light scattering formulation. So basically, the observed optical characteristic of cosmic dust indicates that grains are likely to be porous, fluffy, as I told just now, and composites of many small grains coalesce together. Due to grain-grain collision, dust-grain interaction, various other processes. And for the first time in 1982, Greenberg for the first time suggested that cometary dust is mainly composed of these fluffy grains. And later, when NASA sent a Stardust mission to collect the sample from a comet, Will-2, then it was found that it was dominated by aggregates, and beside aggregates, also some solid silicate particles are also observed. And measurement of recent measurement by this Rosetta mission, which actually visited comet Churyumov-Gerasimenko. So in that comet also, it was found that the comets are dominated by aggregates. Just look at this picture, that whenever incident unpolarized light from, suppose we are considering the unpolarized light from our own star, sun. Sun light is unpolarized. So whenever unpolarized light falls on the surface of a cosmic dust, it actually scattered in different directions. And if we measure this scattered light, we will find that the scattered light is partially polarized. Okay, so unpolarized light after scattering becomes polarized, and this particular dust, this cosmic dust, actually acting here as a polarizer. So this is a very good technique, because if we study the polarization properties of dust, that then it can inform that it can give us information about the many information about the light scattering behavior of cosmic dust. Now I am going to geometric albedo. Repeatedly, I was talking about the albedo of the particle. What is albedo? Basically, in astronomy, geometric albedo of a celestial body is the ratio of its actual brightness as seen from the light source to that an idealized flat, fully reflecting diffusive scattering with the same cross section. So this is the actual definition of geometric albedo. So for your reference, I'm just telling you, Moon has a very low albedo around 0.07, while Venus has a very high albedo 0.60. Basically, geometric albedo is close to 1 for ice bodies, and close to 0.1 or less than that whenever you consider the very absorbing particles. Okay, that's why Moon is sometimes Moon is also absorbs the light which is coming from the sun, and part of it is reflected. That's why we can see Moon every night. So this is only because the Moon is scattering light, but basically Moon absorbs the maximum portion of the light and only sends some of the light to our Earth. But if you look at Venus, you know that Venus is one of the brightest objects in our solar system, which has a very high albedo. What does it mean? It means that whatever light is falling on the surface of Venus, it is actually 60% of the light is actually scattering by Venus. That's why it is so bright. And if you look at other planets like Jupiter, then Saturn, Uranus, Neptune, so they have different albedos. But if you go to the satellites of Jupiter, Europa, the geometric albedo is close to 0.9. So these are the things we should understand. And here you can see that whenever light comes from comet or asteroids and from the sun, you can see that the light is scattered, and because unpolarized light is coming, after scattering the light becomes polarized. And here this is the theta is the scattering angle, and here this angle is the phase angle. Okay, so this scattering actually depends on the scattering angle. So this scattering angle varies from 0 to 180 degree. Now we define the polarization. What is polarization? I think you know that when we consider polarization, we are considering the vibration of the electric light components in a particular direction. Okay. So linear polarization is defined as I perpendicular minus I parallel. What is I perpendicular and I parallel? It is basically the polarized component perpendicular and parallel to the scattering plane respectively. So this value varies from -1 to 1. -1 means minus 100%. Less than equal to 1 means 100%. So why this negative sign is coming? It is only the sign because of our convenience. When I perpendicular is greater than I parallel, then it will become the sign is positive, and otherwise it is negative. And if both of them are equal, remember polarization is 0. So these are the condition which need to be satisfied when you are considering linear polarization. So now I have defined what is albedo, what is linear polarization, then I am going to the next part. So if we study comet and as polarization properties of comets or asteroids, this is the common things. As I just now told you that comet polarization depends on the phase angle or scattering angle. You can see that at 0 degree, the polarization is 0. Then if we further go to 10 degree, 20 degree, you can see that at 10 degree, this negative polarization is noticed, that is known as P mean. Then again, around 28 or 27 degree, polarization becomes 0, and then it shows this type of trend. And this is the dumbbell shape, and you can get a maximum value P max. And this P max is very, very important because in our study we will consider the P max. P max means polarization maximum. So there is a angle close to 90 degree, you will get the polarization maximum, and at around 10 degree, you will get the polarization minimum. Okay, so these are the common properties of almost all comets or asteroids, and these are actually we have studied more than 2000 comets with polarization data, and the same feature is observed for almost all comets. So this is a common phenomena for comets. So Russian physicist Nikolai Umov in 1905 for the first time have come forward with his idea, but he was actually applied to moon and asteroids, and he told us that the brighter powder, the lower its linear polarization. So this is exactly the statement of his paper, which was published in 1905, where he told that the brighter powder, the lower its linear polarization. What does it mean? It means that highly reflective objects tend to reflect mostly unpolarized light, and dimly reflective objects tend to reflect uh, polarized light. So this is the statement of this formula. So what does it mean mathematically? If we want to use this formula, so mathematical formula is PR is proportional to 1 by A. So this is what he has suggested. It means that if albedo is high, polarization is less. Okay. So in 1960-1970, the qualitative law was quantified, and you can see that log Pmax is linearly dependent on log A. So this is the Umo effect for moon. So the astronomer had taken observation of this Pmax and albedo at different position, and you can see that at different wavelength they had considered, and they found that it follows this type of trend, linear trend. And what is the albedo? Albedo is 0.00, 0.05, and these are the 22 various sites on the moon. They had taken the data, and this is nicely showing a linear trend. It shows that if log A is decreasing, it means that log P max is increasing. Okay. So before going, now we are actually applying this particular Umov law in comets also. We have found that comets show low geometric albedo of the particles, and it is close to 2 to 10%. Okay. Now, recent works on Umov effect, I am not going to detail. Various authors, mainly Jupko, Ital, and Group, have studied the Umov effect for different types of particles, irregularly shaped particles, but they had not considered the effect of porosity, because porosity is very, very important in our study. So here we will actually explore the porosity effect. So this is the aggregate dust models. So this was actually generated with the computer code, and particularly recently, this paper last year, this paper was published. So I'm just showing you some of our observations, some of our results which we actually observed. So these are the structure created by computer codes, and you can see that these are grapes-like things, and these are basically cosmic dust with three names are there: BA, BM1, and BM2. You can see, but here porosity is different: 0.87, 0.74, 0.64. So remember, the porosity is a quantity which will tell you about the fluffiness of the particles of a structure. So porosity is 0 for compact particles, okay, and it may go up to 1. So 0 to 1. So here you can see that the porosity of BA structure is very high. It means that it has very porous positions in this structure. Here porosity is decreasing. Okay. So here porosities of the aggregate is defined as P is equal to 1 minus Bi by V. Bi means the internal volume of the particles, and this B is the total volume of the particles, and here Am is the radius of the small particles. We call it monomers. Okay, and based on this, actually we have made our structure. So this is how BA, BM1, BM2 structures are called. These are actually shown here for our computational purpose, because we will be showing you computational results. And here you can see that for each aggregate type, we have considered three structures, 1, 2, 3, like BA, and but they have the same porosity, and their effective radius is same, but they have different porosities. But these three structures are having the same porosity. Okay, so in brief, we should tell you that we are considering three structures with different porosity, but their characteristic radius is same. Characteristic radius means if we consider the radius of the particles as a whole, the average radius of the all three particles are same. And numerical computations were actually done with the help of T-matrix code, which is a very popular code developed by Michael Mischenko, but unfortunately he expired last year. But his code is very popular. Light scattering code is very popular among the light scattering community, and we use that computer codes in our calculation. But let me tell you that this computation takes lots of computation time. Sometimes from 8 hours, 10 hours to sometimes it takes 4 days, 5 days for each computation. So this is a challenge for light scattering community. Because it is taking lots of computation time, and we need a cluster computation or parallel computation to execute the code. Though it looks very small, but even if you want to execute the code with 1 micron particle radius, then it will take around 12 to 24 hours. And if you are going for 4 micron or 5 micron particle size, it may take 15 days to 20 days. So you need a very high computation facility, and we have taken help from IUCAA Pune, PRL, and IIA, Indian Institute of Astrophysics. So these are the three points where computational facilities are there, computation facilities, and we are taking the help of IUCAA, PRL, and IIA Bangalore, and we are very helpful to them for allowing us to do our computation. So here geometric albedo is this is geometric albedo formula through which we calculate geometric albedo from the scattering code. And this, first of all, I will show you the result of the silicate composition. Yeah, so let me tell you that basically, if you look at comet dust or asteroidal dust, the maximum dominated composition is basically silicate and carbon. So here I will show you the result for silicate composition. So these are the repetitive indices value, and here we are considering only two wavelengths, 0.45 and 0.632. And you can see that I am showing you the results here. The effect of porosity, you can see that whenever porosity of the particle is changing, means it is BA, BM1, and BM2, you can see that it is an effect on the porosity. A linear relation is observed in case of this. So this is at this is at 0.45 wavelength, and this is at 0.6. But in both the wavelengths, the nature is almost same. What does it mean? It means that the polarization is decreased whenever porosity is decreased. So this is the conclusion we actually arrived from our study in both the cases. So this is the effect of porosity. We have also studied the effect of size parameter, aggregate size parameter. Means if sizes of a particle is changing, size of a cluster is changing, how it affects the computation here. We have also found out the linear correlation, and this was actually considered in case of this is actually considered in case of BA aggregates, and you can see BA, BM1, and BM2 both are there, and you can see almost the same trend is there for all the aggregates. So it means that if you increase the size of the aggregates, it will actually basically linearly correlated. This is effect of composition. If you change the composition of the particle, like 1.6 is the silicates, and this is 1.9 is the carbon, you can see that this also changes with the absorptive parameter. So again, you can see that there is a linear correlation between them if you consider the effect of composition. Now, recently we had started computing the result for carbon, and you can see here that in case of carbon, very nice fit is observed at wavelength 0.365 micron. It means that whenever porosity of the particle decreases, the polarization decreases, but what happens? Uh, albedo is increased. So this is what we have arrived in our conclusion. Very soon we'll be going to report this work. I'm just showing you one of the such slides. Some other studies are also there, which I'm not showing here because we'll be going to report this paper very soon. My conclusions are like this. We have investigated the effect of porosity in the Omo effect. We have found a strong correlation between porosity and albedo, and we have also studied the effect of size parameter, which in linear correlation is observed. And we have also studied the strong dependence of repetitive indices, and also we have studied carbon aggregates, carbonates, which are showing also similar results. So I am very sorry I have finished the talk before 15 minutes. So the session is open for question and answer. I think it will be better if we go for some discussion. Over to Chairperson, Madam.
Thank you so much, sir. It was a very nice talk. So now the session is open for discussion. If you have any question, you can unmute yourself and you can please ask. I don't see any question in the chat box, so the participants can unmute themselves and they can ask the question. Um, it seems there is no question, sir. So
Yes,
everything is
ma'am.
very clear. You
Okay,
presented
madam. Thank you
in
very
a
much.
nice way that everyone understood everything.
Okay.
Okay, sir.
So with
Thank you
that,
so much.
yeah, thank you, madam, for your. Okay, so I'm unsharing the screen.
Okay, sir. Okay. Well, so the next talk will be delivered by Sri Bhattacharya. Her
Yes,
title, yeah, Sri, you are here, right?
yes, ma'am.
Okay. So the title of her talk is an outline of the X-ray transient universe. So Sri, you have 15 minutes.
Yeah.
Yeah, you can start sharing your screen.
Okay. Is it visible?
Yes, yes. Yeah, please go ahead.
Okay. Good morning, everyone. I am Sri Bhattacharji, first semester PhD scholar under the supervision of Dr. Biplab Sarkar sir from the Department of Applied Sciences, Tejpur University, Assam. Today, the title of my talk is an outline of the X-ray transient universe. And first of all, I want to thank the organizers of Northeast Meet of Astronomers 7th edition for providing me an opportunity to deliver a talk today. So the outline of my talk is here I am going to discuss about the discovery of the X-ray transient universe and its several types of the several types of the transient sources like the high mass X-ray binaries, low mass X-ray binaries, soft X-ray transients, etc. The main aim of my talk is to discuss the overview of the X-ray transient universe in a very brief way. So, the first topic is the discovery of the X ray transient universe. The Centaurus X2 was the first X ray transient source that was discovered in the month of May 1967 during a rocket flight experiment. And it was not, and the same experiment was done 2 years previously in that very X ray region or the X ray wave band, but it was not there at that time, and then it got completely disappeared 4 months later, that is in the month of September 1967, and then reappeared in 1968. And this behavior of sudden brightening and dimming is called the transient behavior. And after the Centaurus X2 came into the light, many scientists gave, and many other sources also started showing such behavior of sudden brightening and dimming. And the transient source or the time domain astrophysics took place, an important place in the observational astronomy. The change in intensity of the transient sources varies typically from a factor between 1,000 or more. This is a figure which is showing a recently discovered transient source from the Rosat observation in the Andromeda galaxy. So, the introduction to the X-ray transient universe. The time domain astrophysics is a new realm of the observational astronomy, and it studies the universe on all time scales from less than a millisecond to more than a decades. In the past few decades, the scientists have done a rigorous research on the temporal variability of the X-ray sources, and it was found that it carries very important information about the nature. And while in general, the transient behavior of the bright X-ray sources indicates an X-ray binary nature, and according to the or on the basis of the mass of the companion star, it is of two types: the high mass X-ray binaries and the low mass X-ray binaries. So, the high mass X-ray binaries, which can be abbreviated as HMXBs, the optical companion here is the BE star, which have a mass of about of greater than 5 solar masses. And in HMXBs, the compact object accrete from the companion star through a strong stellar wind, due to the presence of the massive companion star. And in this configuration, the optical luminosity of the companion star dominates the total emission from the system, and the rate of mass transfer is characterized by the strength of the stellar wind. The HMX possesses longer orbital periods in the order of some days than that of the LMXBs, which have orbital period in order of some hours only. This is an artistic image of the high mass X-ray binaries, from which it can be seen that the mass from the very massive companion star is being accreted to the compact object through the stellar wind, and no distinct accretion disk is forming here, as because the accretion process is occurring through the stellar wind. And in most of the HMXBs, the compact object is found to be neutron star, which have a very high magnetic field, and it tends the matters to funnel through the poles of the neutron star, and we get a very high intensity of X-ray emission through the poles of the neutron stars. Now coming to the low mass X-ray binaries, which can be abbreviated again as the LMXBs. The low mass X-ray binaries contain a neutron star or black hole as a compact object, and a low mass star is a companion star, and which has a mass less than 2 solar masses. The mass transfer here occurs through the Roche-Lobe overflow, and the matter squares through the Lagrangian point after the Roche-Lobe gets filled over with the matter, and the X-ray emission of which predominates the optical and UV emission of the binary system. The LMXBs are less likely to show eclipses, but it often shows some dips, which occur when the line of sight to the X-ray source is blocked by the accretion stream or by the material squirting of the accretion disk when the gas stream hits its outer edge. This is again a artistic image of the low mass X-ray binaries, and here we can see that the mass is being accreted from the low mass companion star towards a compact object, and due to the presence of the rotational angular momentum of the inflowing matter, it is forming a disc-like structure around the compact object, and it forms a Roche lobe kind of behavior. This is called a Roche lobe, and this is a Lagrangian point, which after filling of the Roche lobe, the mass gets squirted through this point. Now, the maximum of the HMXV transients are recurrent X-ray pulsars, and in which a strongly magnetized neutron star in an eccentric orbit periodically confronts a stellar wind zone around a massive companion. The LMXP transients are characterized by episodic X-ray outbursts without any fixed periodicity, and they are in quiescent state in maximum period of their lifetime, where the accretion activity is very less, and occasionally they undergo some dramatic X-ray outburst. And during an outburst, they show a soft X-ray spectrum characteristic of the high luminosity LMXVs, and they are known as the soft X-ray transients, or sometimes they also can be referred as the X-ray nova. The soft X-ray transients are basically the subset of the LMXPs, which contains either a weakly magnetized neutron star or a black hole. And these are the X-ray binary systems that have long period of the quiescent state, which is interrupted by the outburst of the low energy X-rays. Basically, during the quiescence period, the material accumulates in the accretion disk until a critical point is reached. And after reaching that critical point, the disk becomes unstable and the matter is dumped onto the compact object, releasing a burst of X-rays. And an X-ray outburst is triggered by sudden onset of the accretion flow onto the compact object and is followed by the decay with the gradual decrease of the accretion rate. Many soft X-ray transients displace the recurrent outburst with intervals ranging from a few years to tens of years, or even it can be longer. This is an image which is showing the quiescence period of the SXT and the active state of the SXTs, and we can see that here some accretion outbursts are being occurred, and this is this is in the cooler state, and the accretion activity is very less in this period, whereas it is high in the outburst period. Now this figure is showing the light curve of the X-ray nova, and it is sometimes shows similar behavior as a dwarf nova, and it consists of four distinct phases, like the rise to outburst, then outburst, and transition into quiescence, and the quiescence period. And they each phases have a corresponding characteristic time scales, and the rise and decline phases we can see that they are very short, whereas the outburst time is intermediate and the quiescence time is longer. And this figure has been extracted from the Ulrich Kohl book, and this is again a figure which is showing the X-ray light curve of the black hole X-ray binary, which is again a soft X-ray transient. This is again showing a fairly common shape with fast rise of few days followed by a slower exponential decay over a few months, and the outburst is most pronounced in the X-ray region with the flush where it is around 100 of the value. And there can be simultaneous brightening in other waveband also, but as we know in the soft X-ray transient, the X-ray are have a soft X-ray spectrum. And in this period in soft X-ray transient, it can be visible only once in a lifetime period. They are so we can say that the recurrence time is aperiodic or periodic. They varies in a very large range. So there are another types of transient sources also, that is the intermediate mass X-ray binaries and the fast X-ray transients. So in the intermediate mass X-ray binaries or the IMXBs, they have the optical companions in the mass range 1 to 10 solar masses. However, these systems are very rare to find because the masses are not very high enough to produce a required stellar wind to accrete the mass from the companion to the compact object. And if they try to evolve through the Roche-Loeb overflow, the mass transfer phase is very short, and sometimes it remains incomplete. Two known neutron star system may be placed in this group, that is the Hercules X1 and the Cygnus X2. Now, coming to the fast X-ray transients, there are a growing number of recurrent X-ray transients characterized by a short outburst with very fast rise times, tens of minutes minimum or more likely, and typical duration of a few hours. And these are known as the fast X-ray transients. These often occur off the galactic plane and are therefore sometimes also referred to as the high latitude transients. Fast X-ray transients are a mix of X-ray counterpart to the gamma ray burst, flares from the nearby coronal sources, X-ray flashes, etc. So let us wrap up our discussion here. So we can say that the study of the extra transient sources helps the astronomers to figure out and characterize the range of binary system throughout the galaxy and how different observing angles, the stars involved, and orbital patterns can all subtly change the behavior of a system can be studied through the extra transient sources. And this studies also helps us to know how plasma is affected by the extreme gravitational or the magnetic fields. And as we know, the HMXPs have a lesser lifetime than that of the LMXP, and so HMXPs are younger. And so, on locating and studying the high mass X-ray binaries, we can track down the kind of star formation that has been occurred recently. Okay, thank you.
Thank you, Sri. So, any questions from the audience?
Hi, can I
Okay.
ask something?
Yeah, please, please.
Hi, Sri. It's a very nice review of Ranjin. So, if you don't mind, can you actually tell, have you decided what you are planning to do next?
Um, Not, completely decided, but we are going through some extra transient universe, or we are working on some analysis parts also of the LAX PC and SXT.
You will be going to do from the observational perspective, right?
Observation. Yes.
Okay. Thank you. Keep it up.
Thank you. Thank you.
Okay, Sri,
Yes, ma'am.
can you hear me?
Yes, ma'am.
Okay, as a first semester PhD student, you have really presented very well the review of all these things. So, you have also decided to work on observational data analysis and all these things, right?
Yes, ma'am.
And have you started a little bit of those?
Yes, ma'am. A little bit of those by watching some practiced videos, workshop videos,
Okay,
and all.
okay. So keep it up. So only one very simple question. Let me just ask you. This transient nature, more or less, what we understand is that the X-ray sources, almost of the X-ray sources, almost all we can say they are transient, right? So
Yes,
this
ma'am.
transient nature of the X-ray sources,
Hmm.
according to you,
Hmm.
by your literature survey or whatever you have studied,
Hmm.
this transient nature of the X-ray sources, to
Hmm.
what property of these sources will you attribute? Because of what?
Please repeat. To what
To
property?
what? Yeah, to what property, physical property or any other property of these sources will
Hmm.
you attribute this transient nature of the sources? What causes the transient nature actually? For all so many sources are there, right?
Hmm.
So, as per your literature review, whatever you have read, have you understood a little bit of this point?
Mm, the optical.
No, we are talking about X-ray only. Yeah, X-ray transient nature.
Okay.
The outbursts and all you have spoke about, right? So, what
Hmm.
causes those things?
Um, the mass that has been accreting from the companion star, these are very violently, they are, and So due to the accretion process, follow some outburst kind of things, and jets are prepared.
Actually, the instability, right?
Yes.
Okay, okay. Thank you.
Yeah. Thank you.
Okay. So any other question from anybody? Okay. So I think there is no more question. Sri, thank you so much, and all the best for your future
Thank you.
journey.
Thank you.
The next talk will be delivered by Ms. Gulabsa Begum Chaudhary. Her title is Orientation of Local Magnetic Field in Low Latitude Dark Clouds. Gulabsa, are you here? Hello, Gulabsa. Hello. I can see her in the list of participants. Maybe some problem at her end. Okay, she has left the meeting. I think there is some connection issue. I think she will rejoin. I think we can just wait for a minute for her. Is that okay, Sanjeev?
Yeah, so she has joined again.
Yeah.
Let's just talk.
Gulabsa?
Ma'am,
Yeah, yeah,
ma'am, I
yes.
lost my connection actually. Sorry for
It's
that.
okay, Gulabsa. Yeah. So it's your turn. You
Yes,
can start. You can share your screen and you can start your presentation.
yes, ma'am.
Yeah. Gulabsa,
Ma'am,
you have
is
15
my
minutes.
slide visible?
Yes, it's
Okay,
visible.
ma'am.
Yeah. Okay, you can start, please. Yeah.
Okay, ma'am. Thank you, ma'am. So, a warm good morning to you all. This is Gulafsha Chaudhary, research scholar from Assam University, Silchar. And the title of my talk is Orientation of Local Magnetic Field in Low Latitude Dark Clouds. These are my talk outlines. So let me start with a brief introduction about what these dark cloud or molecular clouds are. These are actually cold and dense region of the interstellar medium, which contains mostly gases, 90% of hydrogen, 10% helium, and many other molecules. And these are considered to be the ideal sites for star formation processes to start. In the right hand side, I have shown an an image of a cloud, which is Barnard 68 cloud. This is how the a cloud looks like in image, and this image is taken from internet. So the star formation occurs at the densest region of the molecular clouds, which roughly contains 10 to the power 6 atoms per centimeter cube. And when the internal gravity of the molecular cloud overcomes the gravitational force overcomes the internal support of the molecular cloud, the cloud goes under gravitational collapse, and the star formation at that site starts. So there is a famous criteria of star formation, which is known as Jeans criteria of gravitational collapse. It says that when the gravitational collapse occurs when the mass of the cloud exceeds a critical mass, which is known as Jeans mass, and I have given the equation of the Jeans mass here. So when the mass of the cloud exceeds this Jeans mass, the cloud gravitational collapse starts and the star formation process starts. So in this study, we are actually going to trace the magnetic field of the molecular clouds because the magnetic field plays a dominant role in settling both mass as well as the time scale of the star formation process. And it is also known to introduce asymmetries into the physical systems, that is the alignment of dust grains which are present in the molecular clouds. The magnetic field is assumed to be responsible for that. So it is very important to study the magnetic field of these star forming clouds. And we can measure these magnetic fields by measuring the linear polarization of the background starlight caused by dust grains. And the orientation of the magnetic field at the dense region of the clouds can be measured through submillimeter polarimetry, whereas the magnetic field at the less dense region, that is the outer envelope of the molecular cloud, can be traced through optical polarimetry. So, as we can see from this diagram, when the background starlight and polarized starlight passes through a dust grain, it becomes partially polarized, and these dust grains behaves as the polarizer here. It gives a clear understanding about the shape and orientation of the dust grains in the interstellar medium. So, from the polarimetric study of these clouds, we can measure the polarization and position angle of polarization, and using which we can generate a polarization map of the clouds, which represents the geometry of magnetic field projected onto the plane of the sky. These are the formulas for measuring polarization and polarization position angle, where here P represents the extent of polarization, degree of polarization, and theta represents the polarization position angle, and Q and U represents the normalized Stokes parameters. So in this study, we have conducted the polarimetric observation of 4 clouds, which are CV17, CV24, CV27, and CV188. The optical polarimetric observations of all these 4 clouds are conducted from 1 meter Sampurnanand Optical Telescope, which is situated at Aries, Nainital. And this 4th column represents the theta GP, that means the orientation of galactic plane over these particular clouds. So from the polarimetric study of these 4 clouds, I have measured the polarization value and polarization position angle, using which I have generated the polarization maps for these 4 particular clouds. This is the polarization map of CV17, and this is the polarization map of CV24. So here you can see, if my cursor is visible, these white solid lines represents the polarization vectors, where the length of the vector represents the degree of polarization, and its orientation represents the polarization position angle. And you can see from this figure, all these polarization vectors are more or less unidirectional, that is oriented along a particular direction. And the average orientation of these polarization vectors represents the orientation of magnetic field of the cloud. That is the local magnetic field at the outer part, or outer less dense region of the cloud. So the average polarization position angle represents the local magnetic field. You can see from this figure, this average polarization is parallel to this line, this yellow dotted line, which represents the orientation of galactic plane over that particular cloud, which is 141 degrees for this particular cloud. So you can say that the local magnetic field for this particular cloud is oriented along the orientation of galactic plane, or we can say that the galactic plane is dominated over the local magnetic field of the cloud. And the same phenomena we observed in case of CV17 also. You can also see here the average orientation is parallel to the orientation of galactic plane. And the same thing we observed in case of CV27 also. In this case also, the local magnetic field is oriented along the galactic plane. However, in case of this particular cloud, CB188, we have seen that the polarization vectors are more or less unidirectional. That is, all these polarization vectors are oriented along a particular direction. However, the average orientation is not parallel to the galactic plane. It is more or less almost perpendicular to the galactic plane, which is 28-degree inclined in this particular cloud. So this difference made us extend our study for some more clouds. So we have collected 13 more star forming clouds which are available in the literature, for which the optical polarimetric results are available in the literature, and the result of which I will be explaining in my summary slides. So to summarize, as I already have mentioned, as revealed by the imaging polarimetry, it is found that in case of CV17, CV24, and CV27, the local magnetic field is oriented along the galactic plane. However, in case of CV188, the envelope magnetic field is almost normal to the galactic plane. So, as I said, we have combined the archival data with our observed data, and we have generated this plot. So, in this plot, along the x-axis we have represented the longitude, and along y-axis, y-axis represents theta offset. So, theta offset is actually the difference between the local magnetic field orientation of local magnetic field and galactic plane. So, this is basically theta offset is equals to modulus of theta envelope magnetic field minus theta galactic plane. So you can see in this figure, it is very much clear that the offset is higher the offset, higher is the difference between local magnetic field and the galactic plane, and lower the offset means the galactic magnetic field, local magnetic field is oriented almost parallel to the galactic plane. So in this figure, it is very much clear that in the longitude range less than 100, the offset is very much higher for this particular range, and also in case of longitude greater than 300, the offset is very much high for this particular cloud also. And this region, longitude less than 100 degree and greater than 350 degree, this range actually corresponds to the galactic center region. So we can say that towards the galactic center, the magnetic field of the star forming clouds has their own local deflection, and there is no dominancy of galactic plane over the local magnetic field of the cloud. However, in this range, that is longitude range from 110 to 250 degree, the offset is considerably low. That means the local magnetic field almost tend to become parallel with the galactic plane. So, thus for now, we can make a general conclusion that the magnetic field of the clouds which are situated towards the galactic anti-center region are dominated by the galactic field, whereas those situated towards the galactic center region has their own local deflection, and there is no dominancy of the galactic plane over the local magnetic field of the cloud. These are my bibliography. Thank you so much.
Thank you, Gulabsa. It was a very nice talk. Now the session is open for discussion.
Okay, I have a small query. Can I ask?
Yeah, please, Senorita, please go ahead.
Okay,
Yes, ma'am.
Gulabsa.
Yes, ma'am.
Yeah, so very nice talk you have given.
Thank you, ma'am.
The only thing I just wonder, you have dealt with so much detail of the galaxy, disk, and inclination and all. So
Yes,
I just want to know what is the distance of this molecular clouds from us. I just want to know this distance range.
Okay, ma'am. The clouds which I have, I am dealing with this study. These are most of the clouds are situated within 500 kiloparsec. Only 3 of them are situated at 1500 kiloparsec. But rest are
Okay, it's very nearby galaxies only,
very
right?
nearby. Yes, ma'am. Yes.
Okay. That's why all the details are very clear. Okay, thank you that much. I just wanted to know.
Okay, thank you, ma'am.
any other questions? Okay, it seems there is no more question. Then Gulabsa, thank you so much.
Thank you so much, ma'am.
The next speaker is Mr. Somik Mitra. He will be speaking about steady state general relativistic magnetohydrodynamics equation flows around black holes. Samik, are you here?
Yes. Am I audible?
Oh, yes, you are audible. You can share your screen.
Okay, sure. So just
Samik,
let me
you have
know.
15 minutes. Yeah.
Is it visible?
Yes, it is visible. You have 15 minutes.
Okay, fine. Thank you. Okay. So dear panel members of NEMA-VII 2022, dear colleagues and the audience, good morning to all. I am Shomik and I am a research scholar at IIT Guwahati. Today I'll be presenting my talk on steady state general relativistic magnetohydrodynamic accretion flow around black holes. So here are my collaborators. Professor Das and Professor Maiti is from IIT Guwahati and Dr. Deingia is from IIT Indore. So these are the brief outline of my talk. So being an astrophysicist, I'll tell you that we always look up for the theory of Einstein's general relativity. And we came to know, I mean, we already know that on 1915, Einstein derived this extremely useful theory of general relativity. And recently, on 2015, we celebrated the centenary of the general theory of relativity. And there is a book by Ferreira. Its name is Perfect Theory. And the interesting statement is mentioned that a century of geniuses and the battle over general relativity. So we already know from history that there was a battle to disprove or prove the theory of Einstein's GR. Now, we have found the evidence, I mean, the stronghold came to this theory when we have found the evidence of the existence of these cosmic beasts in the night sky. Those are the black holes. So the primary motivation that we get is to observe black holes. Now, what makes these black holes special? So black holes are black, we know, and they do not emit photons. So it makes them difficult to observe. So the only way to observe them is to follow the infalling matter, what you are seeing in the left-hand image, which is interestingly the first ever visual evidence of any supermassive black hole. And this particular one is situated at the center or the heart of this M87 galaxy, where you can see at the central dark region is the black hole and the surrounding luminous part is the plasmas around it. And this is observed by this Event Horizon Telescope group on April 2019. Now one can ask how this matter is infalling. So that dynamics is governed by the huge gravitational potential of this compact object, the magnetic fields into these frozen into these plasmas, and also additionally the radiation pressure. So you can see this kind of disk structure will form. So I'm not going into detail because yesterday Dr. Shorkar and Dr. Dehingya, they have mentioned it elaborately. So what is more that we know that from this M87 galaxy, we can see there strong jet which is ultra relativistic jet that is coming towards us. That you can see in these two images. One is in radio one and another one is this optical wavelength. So this ejection of matter is also there. So both the phenomena can only be explained if you take magnetic field into account. So there is a toy model by Dr. Dehingya. So here if you imagine there is a three-dimensional model and you cross-section it, you take a cross-sectional view of it. At the center there is a black hole and there is some matter surrounded by it, and you probe a weak magnetic field somewhere. So if you give that poloidal kind of magnetic field into the system, you can see there is jets, winds kind of thing as forming, that is the outflow. And also you can see a stable accretion disk, which is this yellow region, that is also forming in this system. So the similar things can be observed if you see a three-dimensional numerical simulation by Professor Hotawa. So here it is showing that the magnetic fields are frozen into these plasmas and it is actually guiding the infalling matter. And if the magnetic field is strong enough, so magnetic fields will prevent the motion of the matter to fall into this black hole, and they essentially throw the matter out by extracting the energy from this disk system to form a jet kind of structure above and below the equatorial plane. Okay, so now we need to remember this past work. So we have to see that, and we already know that magnetic fields are ubiquitous in universe, so accretion disk has to be magnetized in nature. So let us consider two differentially rotating layers in the accretion disk. So we can understand that there is a viscous torque because there is a rubbing against each other between these layers, and they will generate the viscosity which will help the accretion to form. So that can be governed by this alpha viscosity prescription. But alpha came to in a more interesting way when Balbus and Hawley showed that a weak magnetic field can tap differential rotation and generate turbulence in the system, which leads to instability, that is the magnetorotational instability, and that can help the angular momentum transporting outwards. That is seen in this image, where this is a time slice, time is moving in the above direction. So you can see when matter is outwards and a magnetic field is actually helping the matter to fall in and transporting the angular momentum outwards. There is also a cartoon diagram. This is spring ball system. This is the Keplerian orbit, and you can see this blue ball as the system is moving, it is eventually going towards the inner region, and the red one is getting outwards much more by gaining the angular momentum developed within the spring. So this spring is actually behaving the same role as the magnetic field does in this picture. So the points that we got here, that we yesterday we have seen that Dr. Shorkar mentioned about the origin of this magnetic field, but still those remains a mystery. And also the roles of magnetic fields in governing these accretion ejection properties is also remains questionable. So, but still we have seen that there is no mentioning about the structure of the magnetic field. So we would like to step into this part, and we would like to address these above questions using this magnetohydrodynamic approach in most general relativistic way to explain the viable magnetic field topologies and all the radiative properties. So we are attacking the problem in two ways. One is the theoretical way, one is the computational way. So mostly I'll be talking about the theoretical approach. So first we need to understand the importance of this work. So this is the left image of the Earth, and there are 8 different points which are forced into collaboration to form a huge effective virtual telescope, which will be the EHT telescope that we know. And this can be able to observe these supermassive black holes at the center of these galaxies. And these are the working collaborators. And they successfully captures this first ever image with their radio telescopes. And these radio images are very expensive and tedious. So they have come up with the alternative approach of these global GRMHD simulations, where you need to start with a hot turbulent accreting plasma around a rotating black hole for a wide range of spin variations. So if you do that, you can get this kind of result. And these simulations are highly dependent on these initial background solutions, where we have a significant scope to contribute, as no steady state solutions are available in literature so far. So we would like to step in, and we would like to develop a steady accretion disk model around these rotating black holes. So meanwhile, it is on May 2021, the Event Horizon Telescope successfully captures the first ever signature of these magnetic fields around this NEMA-VII black hole case, and they have shown that the magnetic field strength will be around 1 to 30 Gauss in the inner horizon region, and the magnetic fields will be dynamically important. So motivating with all this, we have developed a thin accretion disk around a rotating black hole of 10 solar mass, and we study the transonic accretion solutions in steady state. So we are assuming only the disk in the equatorial plane, so where the magnetic fields are only this radial and the azimuth toroidal part, which are threaded in the disk midplane, and they are frozen into the plasma by considering this ideal MHD condition. So for Carr black hole, we know this is the metric element and it has a T5 symmetry. So for that, if you want to solve these governing conservation equations of GRMHD, these are the equations. And these are highly coupled nonlinear equations. These are a set of 12 equations. But using this symmetry, it will convert to a 6 set of equations, which we have to solve. And for the matter and the magnetic field counterpart will come from this energy momentum tensor. This part is given by the general relativity part, and this is the magnetohydrodynamic part. So we solve it and we have the results. So when we want to observe this accretion physics, we need to plot this Mach number, which is the ratio of radial velocity over the sound speed. So we know when the, and this, okay, so let me tell you, this black hole is sitting at the origin of this coordinate system, and this radial coordinate is away from the black hole. So when the flow is entering from very far away, it is subsonic in nature, and as it enters towards the black hole, it has to be subsonic. That means with the velocity of light. So meanwhile, it is understandable that there is some point where it changes its sonic property, that is known as the critical point, and that is elaborately mentioned on earlier by Dr. Shorkar. So what is more here, that we change the magnetic field strength at the outer edge of the disk, and we can see that the topology of accretion disk is changing, and at some point of time, it is passing through the outer critical point, which is very important. So these kind of solutions are not reported earlier in literature, so you will be the first one to report these solutions in GRMHD framework. Also, it is expected that in presence of magnetic field, the angular momentum transport will be there, that is seen in panel C. And also this is sufficiently hot, it is going above 10 to the power 11 Kelvin. Now, for the magnetic field counterpart, we have seen that if you measure the magnetic field for the non-rotating black hole in this in Gaussian units, you can see it is going around 10 to the power 5 to 6 Gauss in near horizon region. Also, this plasma beta parameter, which is the ratio of gas to magnetic pressure, that can be showing a interesting results that beta is going to be around 1 in the near horizon region. That suggests that magnetic fields are dynamically important. Now, if we say the contributions of the magnetic pressure for the radial and the toroidal component, we can see the solid line represents the toroidal radial component, and this dashed line is the toroidal one. And toroidal one dominates the entire region except in near horizon region, and that is also expected because in the inner near horizon region, only radially infall can be possible. That is governed by the gravity, and also if radial magnetic field strength will be there only. Now, finally, one needs to measure the viscosity developed within the system. So that we measured using this Maxwell trace over the gas pressure, and that came to be radially varying, which seems to be very interesting. And all our results are in favor with this Event Horizon Telescope group and also the global GRMHD simulations. And we have seen that toroidal magnetic field seems to be playing a dominant role over the radial magnetic field in controlling the accretion mechanism. So finally, I am concluding this by saying these steady state results are always important, because if you have a steady state result in your hand, you can give this to input to start a more realistic 2D or 3D GRMHD simulations, because the GRMSD simulations need initial seed solutions. And also, once you have these GRMSD simulations in your hand, you can actually try to understand the more micro details as well as macro details of this system. And this needs high computational facility. And you can see there is a representation where we have seen that this initially when you give a magnetic field to a matter, essentially it forms a stable accretion disk, and the disk gets very turbulent in nature. So thank you, and you can find me in this page if you have anything to discuss. So thank you. And thank you, NEMA, for giving me this opportunity to present in this platform.
Thank you, Samik, for your nice talk. The session is now open for discussion. Any questions from the audience? Any questions? Okay, it seems. Okay, there is a question in the chat box by Pramod. After many years, is universe goes inside the black. I think Pramod, you wanted to write black hole. Samik, can you see the question in the chat box?
Yes.
Yeah.
Okay, it is not very clear, but actually, universe. I mean, so in different. I mean, inside an universe, if you consider, there are lots of different black holes are sitting because there are lots of different galaxies are everywhere. So at the center of most of the galaxies, you can expect there is a supermassive black hole sitting. So it is not very clear to say whether we can see, I mean, tell that universe will go inside that black hole or not. But essentially, if some matter is passing at certain distance nearby the black hole, it can enter into these black hole systems. That I can say.
Oh, sir, can you tell me? May I ask one question?
Yeah, please.
Okay. So Samik Mitraji, you have used energy moment tensor in your research work.
Yes.
Okay. What can you say about the properties of the energy momentum tensor?
So the covariant derivative of this energy momentum tensor has to be zero always.
Yeah, we have saw that this is energy momentum tensor satisfy conservation equation. Okay, I agree.
Yes.
That means we have to find out pressure density of this equation, right?
Right.
Yeah. Does it satisfy dominant energy condition, strong energy condition, weak energy condition, or can you find equation of state of your research work?
Sorry, I couldn't hear. Can I find equation of state?
Okay, or you can equation of state.
Yes, actually, we have. I mean, this has nothing to do with this equation of state. Equation of state will come from this plasma theory. You can actually use some temperature model like P equal to K rho to the power gamma for adiabatic model. So those kind of thing we have assumed. So particularly for my work, I have assumed this relativistic equation of state, which I haven't shown here. So that is there is a relation between this pressure and the density profile.
Okay, does pressure density satisfy dominant energy condition, strong energy condition, and weak energy condition?
I actually don't know about this.
Do you find out pressure density from the energy momentum tensor?
Yes, I can find that. But there is also another relation you need to use for the thermodynamical part.
If you found out, say, the pressure density from your energy momentum tensor,
Yes.
You must be able to show dominant energy condition, strong energy condition, weak energy condition. This is very important in your research.
Okay, so when you have this conservation law, you can actually project your conservation equations in the fluid frame.
Okay.
So if you project your conservation equation in your fluid frame, like along the velocity line, fluid line, then you can actually get these energy equations from there.
Okay.
So in general relativity, you have to do always with that. So if you do that, you can get all the things you need. Okay. So there will be something like U mu, del mu, T mu nu that you need to do.
Okay.
So if you solve that, there you will get an energy equation. From there, you can say anything about entropy. You can say the thermal quantities and all these things.
Okay, energy equation of state.
Because you have seen here that I have represented this quantity, this temperature I have plotted here.
Yeah.
Then I have plotted one thing that is known as this Alfvénic speed, which is actually the ratio of gas to magnetic field square divided by the density.
Okay.
So I have all the data that can be generated. I mean, the results can come out by solving all these equations simultaneously.
What are the importance of Kerr matrix in your research? Why don't you take De Sitter, Kerr Newman? Because you have to use electromagnetic field equation, right? This one.
Right.
Right. I mean, in this,
So if
you have mentioned Kerr matrix, right?
Yes.
So Kerr matrix is absent of charge because you have used in the field equation there is a charge equation. How do you explain?
So first of all, if I use this ideal GRMHD condition, so there in the so all the calculations are done in the co-moving frame. So if you are in a co-moving frame, and if you remember in relativistic transformation law, if you have a co-moving observer, it won't observe any electric field within this system. It will only see the magnetic field.
Because
And
it should
then
be, to my knowledge is concerned, this your metric should be charge metric like Kerr-Newman.
Yes, you are right. You are right. You are right. But here you need to understand one thing, that we are dealing with this kind of turbulent system where you are not dealing with a single particle. You are dealing with a fluid that is a continuum. So you cannot differentiate everything at a single point charge. So you need to consider it as a continuum mass, right? So if you consider it as a fluid, you cannot use actually those huge number of charged particles in the system. Because you know that there are Avogadro number of charges, and there will be multiple of Avogadro numbers of charges can be there in these huge systems, right? I mean, if you consider this kind of structure and all this, so individually, if you track down a single charge, it will be very difficult to study the entire picture.
Okay.
So other than that, what you do, you remove the charge. So that's why in accretion mechanics, accretion dynamics, we are not able to study these charge particles distinguishedly. But there is a scheme recently that is also a growing field, that is the peak simulation, where that is a particle in cell. So there you actually can use plasma's kinetic theory. So if you use kinetic theory, you can actually follow a single particle into a box, and there you can follow the motion of that particular particle itself. So those are very expensive study.
If you use charge black holes, I think your finding will be more interesting now.
But I don't think there will be lots of differences we can see, because it will be difficult to follow because you need high simulations for those kind of things. But yes, someone can try.
Okay. Thank you.
Okay.
If I am allowed, I want to comment one thing regarding his query.
Okay. Yeah, please.
Okay.
Yeah, so basically the energy condition you are talking about, we really do not care much about the strong energy condition or weak energy condition. But in reality, what may happen inside the ergosphere of the Kerr matrix, this strong energy condition probably may not valid here. That's what I can say. But we really do not care about the energy conditions here while doing these calculations.
So can I comment once again?
Yes, please.
So I think the motivation of this work is just to see how we can reproduce observations, and observationally we can only see photons, nothing else. So all these energy conditions and things are really, as Indu pointed out, it's somewhat irrelevant in this picture. Morely, we require the thermodynamical quantities, how they respond to the system.
Okay. Okay. Thank you, Samik. I think we can now proceed towards the next talk. The next talk will be delivered by Tanus Kumar Thor. The title is Imaging Photometry of the Unusual Comet C 2016 R2 Pan-STARRS. I don't know whether I am reading it correct or not. Tanus, are you here?
Yes, ma'am. Am I audible?
Yeah. Yes, you are audible. You can start sharing your screen and you can present. You have 15 minutes.
Hello.
Yes, Tanis, your screen is visible.
Okay.
You can
Thank you.
start.
Thank you, ma'am. Thank you, ma'am. So my topic for today is imaging polarimetry of unusual comet C2016 R2 Penstars, and I am Tanuj, and I am working under the supervision of Dr. Himadi Shekhar Das in Assam University, Silchar. Now it is working. So let us give a small introduction about the comet. So what are comets? We know comets are small celestial bodies which have several kilometers in diameter, and mainly the constituents of a comet are water, ice, rock, etc. So these are two beautiful pictures of the comet Hale-Bopp, which was taken in 1997, which was happened to be the brightest comet in last few years. So this is the structure of a comet. The three major parts of a comet are: one is nucleus, which ranges.
Tanos, sorry, I think your slides are not moving.
Now, is it moving now?
No. Yeah, yeah, now it is moving.
Okay, okay. So let us
Maybe it is
discuss
not
on.
in the presentation mode.
Yeah. Oh, can I continue from here? If I'm going for the slideshow, then I think the slides are not visible.
Okay, no problem. Yeah.
Okay. So this is the structure of a comet, which has basically three major parts. One is the nucleus, which is the range from 1 to 10 kilometer, and that is the second part is the coma, which is around 10 to the 4 to 10 to the 15 kilometer, and the third part is the tail, and the tail can be of two types. One is the iron tail, and one is the dust tail, which we call a type 1 tail or a type 2 tail. And basically, the tail is always directed away from the sun, and it may extend up to several thousand kilometers. These are some classification of comets. These are two basic classification. One is non-periodic comet, which is comet Levy, Austin, etc. Periodic comets, which has eccentricity less than 1. Periodic comets are further classified into two types. One are short period comets, which has a which is typical periodicity of 200 less than 200 years. Halley is the example. Long period comets are Hale-Bopp, and also the comet which I am taking for this polarimetric study, this is also a long period comet, and it has an periodicity around 20,000 years. Short periodic comets, we have further type of Halley type or Jupiter family comet. Jupiter family comets are those comets which have very short periodicity. One example is 24P Shubha. So we have also taken observation of this comet, which has a typical periodicity of I think 8 to 9 years. Now, this is the common question why you study comets. So, what we think the comets are the remainders of the material formed in the coldest part of our solar system, and we some believe that they brought water and a variety of organic molecules to the Earth. The isotopic ratio of carbon 12 and carbon 13 in comets is equal to 90, which is same as the solar system value. And so, we believe that studying of comets may offer information about the primordial materials of origin in solar nebula, which formed basically 4.5 billion years ago. Now, this is the comet dust, which basically is typically present in the tail of the comet, ending in coma. So, dust particles always scatter and absorb the incident radiation. The scattered radiation makes the dust tail of the comet visible. We do the polarimetric observation and the polarimetric study and observation. Polarimetry is a good technique which we use to study basically the properties of a cometary dust. Now, cometary polarization is basically produced by two mechanisms. One is scattering of sunlight by its dust particles, and one is the fluorescence emission by the cometary molecules. So, this is something when we have a schematic, artistic presentation of a comet dust, where we have the incident polarized light, then cometary dust, and then we have the scattered partially polarized light. Now, what is the nature of a cometary dust? There are several theories. First of all, we thought it to be a spherical nature. There are many papers on thinking comet dust is a spherical particles. Then came as a spheroidal particle concept. And nowadays, what we think about that comet dust consisting of aggregates of monomers. These are some typically two types of monomers which may be used for modeling purpose. So one is BPCA, where we call it ballistic particle cluster aggregates. This is a aggregate which is having 120 numbers of monomers. And the second type is ballistic cluster aggregates, which has MN1 numbers 120. Here it is 120 numbers of monomers. We use this to model the phase polarization versus the scattering angle, that is phase dependence of polarization. So here one work on the observed linear polarization on comet Hyakutake, where BPC and BCCA class aggregates were used, and the refractive indexes derived from this analysis correspond to a mixture of both silicate and organoids, and which is also a good agreement with the in situ measurement of comets of different spacecraft. We can see here a negative polarization branch, which we further study here. The negative polarization of comet Hale-Bopp was studied at a wavelength of 0.485 micron and also at 0.684 micrometer. And here also ballistic particle cluster aggregates and ballistic cluster aggregates were used. And the best fit values corresponding to again a mixture of silicate, mixture of a cometary dust field. So aggregates giving a good fit value for both for the positive and negative polarization of a comet. Now, these are the techniques of observation. We use a telescope, we use a polarimeter, and a CCD, of course. This is something for a typical telescope of a reflecting and refracting type of telescope. Obviously, we use the reflecting type of telescope. This is the sum of the information and orbital elements of our comet C2016 R2 Pan-STARRS. The comet was the first discovered in 2016 in Pan-STARRS 1 telescopes. The object was confirmed as a cometary on the same year. It is a returning long period comet, and of course, it is in post-perihelion stage. Its perihelion date of perihelion was in 9th May 2018. The comet was at the closest proximity from the Earth in December 2017, and it possessed the lowest apparent visual magnitude in that month. We luckily did the observation on December 22 and 23 when it was the brightest object in our sky. These are its orbital elements. Its perihelion distance is 2.6 astronomical units. Aphelion distance is 1,500 something. Orbital period is 21,623 years, so it is a very long periodic comet. Its eccentricity, orbital eccentricity is near about 1, and its closest approach was 23rd December 2017, and on that day we did the observation. Its closest approach to the Earth was around 2 astronomical units. So this is the place from where we have taken the observation of this comet. The comet was observed from Ares Sampurnan telescope. The comet was observed at phase angles of 7.5 and 7.8 degree. And of course, whenever the phase angle is below 20 degree, we expect a good value of negative polarization. Here in this case, we are also expecting a negative polarization value. These are some of the raw images of the comet, which were taken on the 2 successive nights from Ares Sampurnan telescope. Now the main question is, why this comets observed? The spectroscopic studies are suggesting that it has a peculiar volatile composition, where CO is being the dominant volatile as opposed to water, and one of the largest nitrogen by carbon oxide ratios ever observed in a comet. The optical spectrum of the comet is also quite unusual. Most major cometary emissions such as C2, C3, and CN were absent in this comet, but it shows some ionic emissions. This suggests that the comet might belong to a very rare group of comets formed beyond the nitrogen ice line. Alternatively, this comet could be a fragment of a large and differentiated trans-Neptunian object with properties characteristic of volatile enriched layers. Some also thinking it to be a low dust comet. Let us see this figure where they have compared, the comparison were drawn between several comets, and we can see that this comet C2016 R2 Pan-STARRS is showing a very different ratio of abundance of carbon oxide and HCl ratios, and all other comets this is very different. So there are several spectroscopic studies already done on this comet and studying the unusual nature of the comet, analyzing the result obtained from the comet from the spectroscopic analysis. But nobody has done polarimetric study of this comet. We have done the polarimetric observation and analysis of this comet. So we use these softwares, basic softwares for using image processing, and also the polarimetric study. This is the intensity map which we got for the 22nd December night of 2017, and we are getting somewhat which we are expecting. The intensity is more or less, the intensity is high on tailward direction. The December 23rd night intensity map also showing somewhat similar nature. Let us go for the intensity profile case. So this is for 22nd December. We can see the sunward and tailward direction. We have analyzed the intensity profile, and we can see that in sunward direction the intensity was less, and the tailward direction, that is in anti-solar direction, we could observe more intensity for this comet. We've done this for the next night, and almost a similar nature was also drawn for both sunward and tailward direction. Then we found out the polarization values and also the polarization map. So we observed, or we got a negative polarization value of -1% for this comet. We know the polarization basically depends on wavelength, refractive indices, scattering angle, and size and shape of the dust particle. We also studied the polarization profile of this comet, and the polarization profile. This is the polarization profile of the comet. We have taken the consideration of up to 20,000 kilometers from the center of the comet. We can see at the center it is around -1.5% of negative polarization. As we go beyond the center, we can see the beyond the comma, we can see the change in the values of the polarization, which is very much in good agreement with all other comets observed. So from this polarimetric study, which we can give a preliminary conclusion that from polarization study, we are getting the result which we can expect from other comets also. Though the spectroscopic study of this comet is hinting about a very different composition and nature of this comet, but by far now, from polarimetric observation, we are getting an expected result of this comet about the composition of its dust particles. And we are doing some further analyzing of this part, and in few days we will come up with a more conclusive, more bigger conclusion in this regard for the nature of this dust particle, of its composition or something. That's all for me today. Thank you.
Thank you, Tanuj. Any questions from the audience? Okay, no questions it seems. Thank you, Tanuj, once again for the nice talk.
Thank you. Thank you, ma'am.
Welcome. We are now proceeding towards the last talk of this session. It will be delivered by Dr. Tebun Ibumgo Shobha Singh. Title is Modified Hawking Radiation of the Super Black Hole in Lorentz Violation Theory. So I would like to request Dr. Singh to present his talk.
Madam, can you hear me?
Yes, yes, you are audible.
Can you see me my screen?
Yeah, you can share your screen.
Share screen.
Yeah.
Can you see, madam?
Yes. Yeah, yeah, it is coming.
Okay, thank you, organizing committee secretary of NEMA for giving me a chance to talk here. And on my colleague, and my talk is modify housing radiation of digital black hole in Lorentz violation theory. But I will discuss about something about the origin of Hawking radiations. Thermal radiation of black hole was discovered by Hawking 1974-75 using quantum field theory in cup space-time. The study of thermal and non-thermal radiation properties of black hole is an important aspect in the black hole physics. In the last few decades, much attention have been paid to investigate thermal and non-thermal radiation of scalar particle, Dirac equation, and Maxwell electromagnetic field equation. Now, yeah, yes. Barik and Wilczek 2000 proposed radial non-geodetic equations. The method, according to his potential barrier, is created by the outgoing particle. Imaginary power of the action is obtained by using semi-classical WKB approximations. They have shown that the spectrum is no longer precisely thermal, and so some information of black hole can be obtained. And Van et al. 2005 as an extension of Padmaban to 1999 discussed the Hawking radiation for extremal rotating black hole using relativistic Hamilton-Jacobi equations, WKB approximation without considering the particle back reaction. Now, recently, tunneling of Dirac particle was investigated by Kerner and Mann for the general non-stationary black hole by choosing appropriate gamma matrix. In this case, we choose gamma matrix from the line element, substituting the wave function and to derive field equation. The action of the radiant particle can be obtained. It is related to Boltzmann factor for emission at Hawking radiation in according with the semi-classical WKB approximation. Now, Kruglov 2014 investigates the Hawking radiation of vector boson particle from the black hole using Hamilton-Jacobi answers to Procca equation WKB approximation. For the Sorsal background geometry, the emission temperature is agreement with the Hawking temperature corresponding to scalar particle emission. Most over the 2000 was investigated vector boson tunneling from the distant black hole in three coordinate system, namely parallel coordinate system, Eddington coordinate system, and the knife coordinate system. Now let us consider about distant black hole. This is the distant black hole in retarded time coordinates, and this is equation number one has four roots. Equation one represents Kerr-Newman digital black hole for lambda equal to 0 and anti-Kerr-Newman digital black hole for lambda less L is equal to 0. Capital M is the mass of the black hole, A is the rotational parameter. If 1 by lambda is greater than M square, greater than A square plus Q square, then lambda equals to give the four real roots, say RC, RS, R plus, and R minus. Specifying this condition, the largest root represent location of cosmological horizon, RS corresponding to location of event horizon, and R plus indicate location of Cauchy horizon. Negative roots R minus represent another cosmological horizon on the other side of a ring singularity at R equals 0, another infinity in accordance with Hawking 1977. Now, this is the electromagnetic field equation expressed in Newman, Penrose, Penrose, Newman and Penrose. Say Penrose got Nobel Prize in the year 2020, and he developed this idea expression of Maxwell electromagnetic field in the Newman Penrose formalism, and d delta are the direction derivatives. Chandrasekhar in his greatest book, the theory of mathematical theory of black hole, has shown that this equation number 2 cannot be separated for charged black hole. So in this topic, I will discuss. I will separate the radial and angular part of this equation number 2 using say by finding say spin coefficients. So now this is the we derive direction derivative of the curve distant black hole, and this is given by this for vector where L and N are pair of real non-terrestrial vector, M and M bar are where complex conjugate satisfying normalization condition L dot M and this one. This is very important. So then we will say, yeah, very important. We use generalized total coordinate transformation. This is equation number 3. This using equation number 3 in this equation number 2, we can separate this equation, and then we will obtain second order form of Maxwell equation near the event horizon. So we derive spin coefficients and from the distant black hole, and substituting to the dynamic equation, we can separate two wave equations from the Maxwell electromagnetic field equation 4 and 5. This Maxwell electromagnetic field equation, by combining this 4 and 5 and approximating this highest coefficient tends to 1, we get circular gravity given by equation number 6. Now then, to study the wave equation, so we can combine these two wave equation to a single equation in order to separate the radial part, angular part. We will use equation number 7 to the combined equation. So we are k theta, k phi are component of generalized momentum of Maxwell electromagnetic field. We use k theta, this, and where S is the Hamiltonian function of Maxwell electromagnetic field equation. Substituting 7 into this equation number 6 and 7, then we will get two wave equation. This represent upper one is the we will get two wave equation, and after that we will get two independent incoming wave and outgoing wave. This represent the upper one represent outgoing wave of the event horizon of the black hole, and the inner one incoming wave. Then say by using Damor-Ruffini, and it can continue from outside the horizon into inside by rotating minus pi to lower half of the complex span. We get this big wave equation. Then relative scattering probability are equal at the horizon of the black hole. This is given by equation number 10. Now, according to suggestion, Damor-Ruffini extended by Shannon-Thamen radiation spectrum is given by this equation number 11. In this is equation number 11, KV is known as Boltzmann constant, and this plus sign in equation number 11, plus sign indicates Fermi-Dirac distribution, and negative sign indicates Bose-Einstein statistics. So equation number 11 shows that a black hole radiates like a black body radiation. So this is the isolation between the radiation of black hole according to Hawking radiation. Now let us take the Lorentz violation theory discussed, because recently recent research on high energy quantum gravity theory shows that Lorentz violation is needed to be modified in Planck scale. Gom et al. 2000 developed a new Lorentz violation scalar equation in which Lagrangian L is given by equation number 12, where M U alpha are the mass of scalar particle in either Lie vectors, and lambda is a proportionally constant. U and U alpha means either Lie vector satisfy this equation number 13. Equation number 13 is very important for studying Hawking radiation of black hole, because either Lie vector merely work on flat space-time, because for choosing say U alpha for the flat space-time from the flat space-time, satisfying this equation number 13 is very easy, but for space-time, so let us discuss. We will discuss in this paper. Now, the scalar equation in space-time in accordance with principle of least action satisfy equation number 14. The ideal Lie vector U alpha may not be taken as a constant quantity in space-time. This is very interesting. One of the one problem of the Lorentz violation theory, because U alpha is a constant, but in the case of space-time like Schwarzschild black holes, Kerr-Newman black hole, Kerr-Newman distant black hole, it should not be taken as a constant quantity. But we can claim that the U alpha say may satisfy this condition. Satisfying this condition, so it's very important for equation number 13 is very important for studying Lorentz violation theory, because we must choose the covariant or contravariant vectors satisfying this condition. Now, either Lie vector may not be taken as a constant quantity in space-time, but it can hold equation 13. So it must satisfy equation 13 in order to investigate Hawking radiation of the near the event horizon of the black hole. For the different black hole, say we must choose that equation 13 must be satisfied. The action of scalar particle in which scalar particle theory and the Lorentz violation is taken into consideration can be written as equation number 15. And from equation 4, then we derive the Lorentz violation scalar equation in the space time. This is extension of Klein-Gordon equation. If lambda tends to 0, it becomes Klein-Gordon equation. In equation 16, constant time lambda tends to 0, we will get original Klein-Gordon equation is recovered. To derive modified Hamilton-Jacobi equation from the modified Lorentz modified Klein-Gordon equation, we shall use wave function psi is equation number 17. Using equation number 17 into equation number 16, we will get where S is in this case is the Hamiltonian function, S is the Planck constant. So we will derive this is equation number this equation number 18 is very important. This equation number this equation number 18. We will derive then Hamilton-Jacobi equation in Lorentz. This is equation number 18 represent Hamilton-Jacobi equation in Lorentz violation theory. This is very important for the research work. Now this is let us consider coordinate transformation. We will discuss 3 coordinate system of coordinate, NEM coordinate system, and parallel coordinate system, Eddington coordinate system. So in a given equation, let us transform d phi by dt equal to g144 by g44, then space time of Curtis-Black black hole in spherical polar coordinate reduced to equation number 19. From equation number 19, how will we choose either line vector to study Hawking radiation of black hole? So in order to do that, we choose say ut equal to ct by square over g11, and u are these expressions, u theta equal to this expression, where ct, cr, c theta are arbitrary constants, and k equal to this satisfying k equal to is given by like this. So now we derive u alpha. This slide is not working. U alpha is what? In this case, u alpha equal to ct square, cr square plus c theta square. Yeah, okay, we can continue further for studying Hawking radiation of black hole. So next, then after some calculation, we find say change in Bekenstein entropy of Curtis-Black black hole due to Lorentz symmetric violation is given by this expression. From equation number 22, we have seen that due to presence of Lorentz violation, Hawking entropy is modified, and when lambda tends to 0, lambda tends to 0, we will get half of the Hawking entropy can be obtained. So this is the limitation of the NEM coordinate transformation, and this limitation of NEM coordinate transformation can be removed by using parallel coordinate transformation, because parallel coordinate transformation, now let us consider this is the to discuss tunneling rate the event horizon of Curtis-Black black hole, the well-defined coordinate system known as parallel coordinate system is considered. Let dt equal to dt, this expression given by equation number 23, where f and g are represent two RBD function. It is obvious that constant time slice is a flat equilibrium space, and taking this one, this known as equation number 25 is known as parallel coordinate system. Parallel coordinate system, it may have many athletic fixture parts. Firstly, metric components are analytic at the event horizon, and secondly, the constant time slice are flat equilibrium space. But it assumes that second one is very important, because WKB approximation may be used to derive tunneling rate, and WKB approximation is obtained from the quantum mechanics of that space-time. Thirdly, there will exist a time-like killing vector field. Lastly, this equation 25 will also satisfy Landau clock synchronization condition, Landau analysis 1975. So this has so many iterative phases than the other coordinate systems from NEM coordinate system. Now, to discuss Bekenstein-Hawking entropy of the distant black hole, we choose either line vector, this one. This is choosing of this either line vector is very important. Without choosing like this, we cannot continue furthermore because it does not satisfy U alpha constant given in equation number 3. So this choosing of ut and u theta and satisfying the condition is very important for studying of Hawking radiation of black hole. Now in the last now after some calculation we can find out the change in Becquerel Hawking entropy of disturbed black hole due to Lorentz violation theory in parallel coordinate system is given by this equation number 27. From this expression equation number 27 shows that Becquerel Hawking entropy is modified due to presence of Lorentz violation symmetry, Lorentz violation theory. So if lambda equal to 0, then we get exact Becquerel Hawking entropy given by equation number 27. And suppose in the similarly you choose Eddington coordinate system, so we will get change in Becquerel Hawking entropy near the horizon of say disturbed black hole is given by same as this equation number 18. From equation number 27, 20i, we observe that due to presence of Lorentz violation parameter lambda, so the Hawking temperature, Hawking change of Becquerel Hawking entropy is modified, but when lambda equal to 0, we get accurate result. We get accurate result because in this conclusion, I will explain the advantage of the Lorentz advantage of parallel coordinate system and Eddington coordinate system over the net coordinate system. We discussed tunneling of scalar particle across the environment of the black hole using Klein-Gordon equation with Lorentz violation theory of space-time in three coordinate system: NEP coordinate system, parallel coordinate system, Eddington coordinate system. The Hawking temperature, entropy, heat capacity are also modified. So actually, in order to derive the Becquerel Hawking entropy, naturally Hawking temperature, saturated gravity, should be modified, and this modified Hawking temperature is due to the presence of Lorentz violation parameter lambda. Lie vector U alpha. It is on the Hawking temperature, entropy, heat capacity. So we assume that from this expression, this modified Hawking temperature will be increased or decreased depending upon the choice of the Lie vector. This is one of the main conclusion of this my research work. So it is shown that Hawking temperature, entropy, and heat capacity increases or decreases depending upon the choice of Lie vector U alpha. When Lorentz violation theory is cancelled, NEP coordinate gives incorrect result of Hawking temperature, Becquerel Hawking entropy, and a specific, but parallel coordinate system, Eddington coordinate system, give the exact Hawking temperature, entropy, the specific capacity of disturbed black hole. The variation between NEP and or Eddington or coordinate system may be seen in the cup manifold. A covariant distribution of the form 1 by R plus iota 0 cannot be derived from the non-locally integrable function 1 by R. In the parallel coordinate, in parallel and Eddington coordinate system, metric components are analytic at the event horizon are equal to RH of the black hole. There is a timeline killing vector field which keep the space-time stationary. Hence, their coordinates are suitable to study Hawking radiation, Becquerel Hawking entropy, and the specific heat capacity of disturbed black hole near the event horizon via Klein-Gordon equation. Thank you.
Thank you, Dr. Singh, for the nice talk. The session is now open for discussions. Participants can ask questions if there is any. Any questions? Okay, I think there is no more questions. Then I would like to thank Dr. Telem Singh once again for his talk.
Thank you, ma'am.
So this was the concluding talk of this session. I would like to thank all 6 speakers of this session. All the talks were very nice. So thanks to all speakers and thanks to all the audience. Thank you all. Now I would like to hand over the session to Sanjeev.
Thank you, Rubjoti. And thank you to all the participants for your kind attentions. throughout the morning sessions very patiently. So mainly thank you again to Rohit Jyoti Gogoi, so for coordinating the morning sessions. And I would like to thank all the others to these morning speakers for their presenting the current works and the question and answers, interactions, and fruitful discussion. So with this last speaker, so this morning scientific sessions ends here. So we'll meet again by 1:55 or 2 p.m. afternoon. So all are requested to make afternoon sessions most confident by joining timely. So till then, I would like to thank you all and taking a break for the lunch. Thank you all.